Hello, welcome back. My name is Jimothy, and I will be going through some free body diagram review as well as some moment review and moments. I find I'm going to start with an example. You can give it a try and go from there. In the example, I will then do a bit of a segue off of moments so that you get a example with an explanation. This is a review, so I find that's the best way to do it when you have a concrete example to look and reference at. So, before you give this problem a try and jump into this, first just try drawing the free body diagram. And the free body diagram, or FBD, remember we want to draw the object or our system. So we're going to draw the D, we're going to draw our system. And if we recall from last video, we have our system. I like to think of it as frozen ice cube. So freeze your system, and then if you were to place that on the ground or in whatever position that you wanted to, then you use that to look at what forces are acting externally. So then you draw the system and draw forces acting on the system. So remember, external forces on that system. So right now is a good time to pause and try drawing the free body diagram. Most classes, a lot of classes in kinesiology or health science that do physics type problems might give you a diagram to start with, but this is good to know to just apply your own skills and see if you can, in case that isn't the case for your program. So pause right now and give that a try. Okay, welcome back. Sorry about that. So to draw the free body diagram, we are going to draw our system, right? First step, draw our system. So we can read the question. Jimothy's doing a push-up with a perfectly straight back. Okay, he is at the top of his push-up with his arms fully extended perpendicular to the ground. So, perpendicular to the ground, I know he's going to be on the ground. We can draw his feet and then his arms. It's going to be a great drawing of him. Oh no. Great drawing of Jimothy doing his push-up, little smirk and hairdo, as always. Right, his arms are perpendicular, so pretend that's 90 degrees. Right, you can even throw in that angle. I'm going to do it in a different color so I don't get confused. That is 90 degrees perpendicular. And we'll give the ground so we can tell that is ground and not some plank floating in the air. So his arms are 2 meters long. So right now, I'm worried about draw the forces acting on the system. So his arms are 2 meters long. That's nice. But then it says his center of mass is 0.1 meter above the ground, and the distance is here. And so knowing that while we're kinesiology majors, we understand the center of mass is roughly around the pelvis, right? And the center of mass, we also know, you can draw it as this logo or not. The center of mass is where your weight is going to act through, or where your mass is going to act through. So we can draw this as force W. So he has a mass of 90 kilograms, and there's a ground reaction force at his feet with an angle of 20 degrees from the vertical. Now, this question is not clear because technically, if I was to draw the vertical, is the force 20 degrees this way or this way? We're going to use our sense and say, when I'm doing a push-up, my feet tend to slide out this way. Therefore, this force is going to be reacting because you have that friction force stopping your feet from sliding. So we're going to say this is the F ground reaction force, and that is 20 degrees from the vertical. And that 20 degrees can be drawn on this side. Both are correct. So we have that force. And now it's saying, but it is, before we even answer this, is there any other third force? What's going to be acting? Well, if we go back to our previous video where we make an ice cube around our system, which we've chosen as Jimothy, because we know, well, we first can show that the ground reaction force at the hands, they kind of give it away. There's going to be some ground reaction force here. So we can make the system Jimothy because that makes this force external, so we can calculate. And if I was to place this ice cube on the ground, right, there's that force at the feet and at the hands. And then there's the weight going down. So we know that there is a force here, but we don't know its direction. And if we recall from the force video, that means there's some mini vector fx and some, or fy, and some mini vector fx. We'll correct that, fy. But we don't know the size of these guys. So what are we going to do? We're just going to assume that there is some force, unknown force fy, and unknown force fx. Assume that is only in the x direction, and that is if we have our coordinate system right here, our x and y. And I assume, and always assume, these forces in the positive direction, no matter what. We will talk about later. Right? And now we have our free body diagram, but if we want, we can add in some distances. So we know arms are 0.2 meters long, so we know that is 0.2. Center mass is 1 meter above the ground. We know 0.1 meter, we know that's 1 meter. And distance between his feet and center of mass is 0.4. So this is 0.4. And we know center of mass to shoulder is 0.3. So we know this is 0.3 meters. So we're given a pretty good understanding of Jimothy and his situation he's in. So in order to calculate this, we have our assumptions: rigid body and static equilibrium, right? Because Jimothy's not moving, so acceleration equals 0. And so therefore sum of forces equals 0. And why does that help us? Because with this full assumption, we have 3 equations. Sum of forces in the x equals 0, sum of forces in the y equals 0, and sum of moments equals 0. And this gives us 3 equations. And if we have 3 equations, how many unknowns can we solve for? The answer is 3. We can solve for however many unknowns we have an equation for, right? We have x plus 2y equals 3 and 2x equals 1. We have 2 equations, 1, 2, and 2 unknowns, 1, 2. So we can solve for x and y, right? But if we just had this top equation, we have 1 equation, 2 unknowns. We can't solve for anything. But we have 1 equation and 1 unknown, so we can solve for it. So basically, the point I'm getting at is, in this case, we'll always have three equations. So at most, we only, at most, can solve for three unknowns. Right? We can keep that there. And the first step, you can technically start with any of these equations, but you can be strategic about it and start with an equation that's going to make your life easier. And in most cases, especially in most classes, that equation that's going to make your life easier is the moment equation. Why? Why is that important? You can, using sum of moments equals 0, allows you to get rid of, we're going to do quotations, of unknown forces. That seems like a good deal. It seems kind of too good to be true. So we're going to figure out why that is. Well, the main thing is that it's a sum of moment around any point. Any point. We only can choose one. You can only use it once, but you can use it around any point. Why? If I choose this point on Jimothy, is he rotating around this green dot here? Is he rotating? No, he's not rotating around that dot. If I choose up here, is he rotating around like his neck? No, he's not rotating in either direction around his neck. If I choose here, he's not rotating. He's not rotating at all. So no matter what point you choose, the sum of moments, or you can think of it as sum of rotational forces, equals 0, right? Because if sum of moments did not equal 0, that would mean he's rotating. And we assume static equilibrium, right? So since we assume static equilibrium, up here, he's not rotating, and so we can choose any point. But before I explain this and get into this, we need to understand and review what moments are and get a deeper understanding. Because this seems great, and it's a great place to start, but you need to know what you are doing. So, we have two equations for the moment. The magnitude method, which looks like something like this, where the two lines around the R and F just means magnitude of cos theta. We'll say mag, and then we'll say cross product, where we have R cross F equals moment. Oh, I don't have an S for cosine. And notice, this is magnitude method, so it gives you the magnitude. This is moment, so it gives you the moment vector. So this does not have direction yet. This does have direction. So we'll get into that in a second. But let's first define everything. R, we'll do a different color. I like purple. R equals moment arm. But that means nothing to most people. So it is the position vector, but that also means nothing, or line connecting the point of rotation, so the point you choose to sum your moments about, to the point of force application. So if I have one of those, sure, I'll draw it this way. If I have one of these wheels, right? It tells me what I'm going to do for the evening, right? One of those spin wheels, and you flick it, and it lands on one of these triangles, right? Pretend I just have the board with a pin in it, and I flick it with some force this way. We can label that F equals force. So if I hit it with the force this way, the moment arm is connecting the point of rotation, the line connecting the point of rotation, which is this guy, to the point of force application. It's applied right here. Therefore, that moment arm is this vector. If we were given the exact, it would be roughly like that. But we're just going to pretend that this is a really thin piece of wood. It's like 0.0001 meters. So very thin, that doesn't matter. So we have R and F. And now we need to define cosine. Cosine is but the angle between F and R. So again, in this direction, this would be 90 degrees. The angle between F and R, and we can say smallest angle, and smallest angle as in not an obtuse angle, has to be acute, right? Like if we have two vectors like this, it's always going to be this angle, never that angle, right? So we've defined everything in here. And so we're going to shrink this up, and we're going to talk about what it does, what each of these equations do. They both multiply perpendicular components of force by distance, or R. Saying perpendicular, why perpendicular? Well, if we look at our example down here, right, we have force applied. And remember, this is a little spin wheel, right? If I hit it with this force, that's going to cause this pinwheel to rotate, correct? That should make intuitive sense to most of us. If I hit it with a force at this direction, it's still going to rotate this way, right? Now, the closer I get to being flat, I hit it here, it's going to rotate, but not that much, until I get to the point where I'm hitting it directly in line with that point of rotation, in which this force, it's not going to rotate either way, right? It's not rotating either way in that case. Why? Because it's the perpendicular force that does the rotation. When I hit it like this, recall we have our Y and our X force. We can call that Fx and Fy. And Fx is causing no rotation. No rotation. It is only Y. So it is only the perpendicular components that cause something to rotate, right? Does that make should make sense. If I hit something in line, if I hit something in line with that axis, with that kind of that point of rotation, it's not going to rotate. It has to be something along perpendicular. So you may be saying, well, how does that make sense? Well, if we look at this equation, we know this equation we normally write as Rx Fy minus Ry Fx, right? And we can say cross product if you draw the x vector or the r vector in this form and the f vector in this form here, we know it does a nice little rx times fy minus ry times fx, which makes a nice little cross. So in this equation, if we do an example, we bring Jimothy back here. If we look in a moment about this point here, we have this position vector to the weight. You can't see that, it's right here. And if I were to draw that here, it's going to be a vector like this with that force vector down here. And we may as well grab Jimothy just so we can see this in action. Right, and we know this vector is 0.3. This is a badly worded problem. But we're going to assume that this 0.3, this is not an assumption, this is my issue, but we're going to assume that this vector, this 0.3, is the x direction. So we know this is 0.3, 0.2. And fx is, in the question, 90 kilograms times 9.81 meters per second squared. And in that, with this equation, what do? We have r, we'll grab f away. We have ry and rx. And f is going to be fx, fy, but fx is 0 because it's purely in the vertical. Therefore, looking at this part of the equation, we have rx multiplied by, well, it's fy minus, and we have ry multiplied by fx, which equals 0. But look, they are perpendicular to each other. Both are perpendicular to each other. So same thing, it's only multiplying those points that can cause rotation. Correct? And if we were to plug this in, right, we have, when doing this, since we have these vector hats, we need to make sure everything is the right direction. So we know Rx is positive, Ry is positive, Fy is negative, and Fx is 0. So we really have 0.3 meters times negative 90 times 9.81 newtons. And that, if we do our math, is negative 264.87. Negative 264.87 newtons. And that's just for the moment this way. But we're forgetting about this next equation. So we will take this next equation and also show that it does the exact same thing, which may be harder to intuitively see, but we know the magnitude of r is going to be square root of 0.3 squared plus 0.2 squared square root, so 0.36, 0.36, and that f, the magnitude, is 90 times 9.81 because it's the only component. And as the only component, it would be fy squared square root, which equals fy. So let's draw it out. We have our r vector and our force vector, exactly what we had before. Now, if we have an angle of theta and we rearrange this equation and we move the r in there, and we notice r cos theta. We notice if I make a triangle, it is sine theta. That is my apologies. I'm thinking of the dot product. Sine theta. That is the magnitude method. Sine theta. In this case, sine theta, in this case, we have a right triangle, and what does r sine theta, r magnitude, which is the length of this vector, times sine give us? We know SOHCAHTOA that the opposite equals hypotenuse times sine theta. And that opposite is this green side, which is perpendicular to that force, right? So we now see that both moment equations are perpendicular to force and that moment arm. So the perpendicular distance just has to be to the line of action of the force. So it just has to be perpendicular to this same line, right? Because in the other method, we had x here, and if the force, in another example, if we have r, and we, let's say, have f here, right, we are going to have, we'll do that in blue, keep consistent, rx and ry. And rx is going to be perpendicular to that y component of force, right? And it doesn't matter that this x is like completely here or up here. It just matters that it's on the same line. So that if they intersect, they are perpendicular. Same thing for y. As long as it intersects perpendicularly to fx, which it does, we're good. And same thing for using the magnitude method. As long as we have this force, we draw this line here, if we are given this line, as long as it's perpendicular, we can use this blue line as r times f. And then it would be r times f times sine, and sine 90 equals 1. So it's just r times f, right? And that's why it's sine, because the more perpendicular, the greater that moment. The less perpendicular, the smaller that moment. So it just has to be perpendicular to the line of action. But both of them do the same thing. And we were just going over moments, and I realized halfway through that that question I made quickly was not ideal to fully answer. So I will be answering that question after I fix the wording in a previous video or in a next video. And I hope this helped with your understanding of moments and where they come from. So thank you, and hopefully you enjoyed it. If you have any questions, leave a comment, ask me, and I will try to answer it in a future video. Thank you.